Hi, I'm Dan Funk. I'm the program manager for the Nuclear Energy Advanced Modeling and Simulation program. And whether you're watching this live or at some future time recorded, welcome. I'm going to give a short overview of the program, and bear in mind it is from a program manager perspective, but we've included, we hope, enough technical detail on each slide so that you can digest it and you can form your questions and get them back to us, either to me or to Dr. Brad Reardon, who is the technical point of contact for our NEAP area, or through him to the rest of the ELC, the Leadership Council for Neams. So we're a program that's resident in NE and under the Office of Science and Technology Innovation, and we feel that we have a good value proposition. For some of you, this is a recap. Others, this might be new. The summary of this slide is that we develop, and more importantly, we deploy advanced computational tools to enhance, accelerate, and we hope fundamentally transform R&D programs, whether they're NE R&D programs or R&D programs outside of DOE or in industry. For us, it's not enough that the tool is developed and demonstrated, that it's proven itself is useful if it just goes into some R&D programs tool chest to be used occasionally. We feel that the real measure of success is that more or less these tools become part of the genetics, the DNA of that R&D program. In any case, that's our ultimate goal and what we endeavor to achieve by our efforts, which you can see outlined on this slide. In this slide, you see the mission areas for Neams. We put this here just so you can get a big picture of how we're organized. The names have not been changed to protect the guilty. We're fully guilty, and we're all here. The codes that are mentioned in this slide are not comprehensive. There's a lot of tools and components in the Neams toolkit that you won't see here, but this gives you a good picture of the overall areas of emphasis. The dotted lines represent our major areas. We have 3 product lines: fuels product line, reactors product line, and integration product line. We'll go over those later. And then we have 2 high-impact problems. High-impact problems is a growing area in Neams, a growing area of emphasis. However, even though it's a separate area, it still makes use of the tools that are produced in the product lines and are covered in the subscope, the work subscopes for this call. And you can see also we have a mission support area where we're currently doing our treat modeling and simulation. And then you see the investments over to the right. And the most important investment is university programs. If I'm talking to the small businesses, I might say the most important is the small business innovation research. And seriously, the university programs comprises our largest investment in this area, and it is very important to us. And here is the pictures of the usual suspects. This is the Neams Leadership Council. This is a team that has pulled together a program that has proven itself to be very effective. You can see my name's there as the program manager. Shane Johnson is the deputy assistant secretary for whom we work. But here you can see Chris Stanek, who's the NTD. You can see and all the other guys that head up those areas, and in the center there is Brad Reardon, who heads our integration product line, but he's also our main technical point of contact for this call and for NEAP projects. So covering the product lines first, the fuels product line. The takeaway from this is that the main obstacle or the main hurdle for coming up with more predictive codes for fuels performance is a better understanding of the microstructural changes and the resulting the resulting mechanical and performance changes of fuel while operating in a reactor. It's not just that, but that's the primary central motivation for our work in this area. We hope that by making these developments that we can better inform future fuel designs and enhance the deployment of advanced fuel designs that improve reactor performance and give us an advantage in terms of accident tolerance and the economics of the fuel in operation. From this slide, of course, you can see the graphics. We go from the atomistic simulation and mesoscale, which are lower length scale, and we use that to feed the engineering scale fuel performance tool Bison. And this is another depiction of that connection, only showing how they both work on the Moose simulation framework, which enables the rapid development of finite element method-based applications. One of the key areas in the fuels product line, or for any of our tools, is validation. So in the case of Bison, we have an example of advanced validation that is underway with the Holden missing pellet surface experiment. We have known for some time that manufacturing flaws, such as the missing pellet surface defect, have actually caused fuel failures. And then it's a nature of those failures that they are three-dimensional. And so consequently, we're developing Bison with three-dimensional capabilities. In order to validate a tool with three-dimensional capabilities, we need to have experimental data that is three-dimensional. And historically, the experimental data has been derived using methods where we have uniformity axially or radially, such that you end up with data that really addresses either point or 1D or at most 2D application. So the idea of this experiment is to use Bison to help to design an experiment that produces three-dimensional data that then is also useful to validating the three-dimensional aspects of Bison. And once validated, we believe that will help us Bison can then be used to develop better fuel and to inform fuel manufacturing tolerances. This would be a significant advantage. In the reactor product line, we have the Sharp suite code, and you can see here that three elements of that code, of that suite. NEC 5000 to address thermal hydraulics, Proteus to address neutronics, and Diablo to address the structural dynamics in the core. I think whereas the nut to crack in the fuels product line was where the microstructural changes in the fuels and in the cladding and understanding the impacts on performance. I think here the nut to crack is to be able to couple widely differing physics that have different time scales, different space scales, different geometries, and to couple them in a way that can be done with high fidelity results. There has been some coupling done, but where they homogenize a lot of the parameters, and it's simplified. It can be useful, certainly can be useful, but for new applications where we would like to see high fidelity simulations with coupled codes, this is the way we're pursuing it. So we call it Sharp 3D, and one of the modules that was not pictured was MC squared 3. So MC squared 3, Proteus, NEC 5000, and Diablo, and they provide us that high fidelity, multi-scale, multi-physics simulation of core dynamics. I think here, oops. Okay, sorry about that. So taking these modules one at a time, NEC 5000, the thermal hydraulics code. It's a computational fluid dynamics tool set. It's currently single phase flow, but we're working to expand it to two-phase. It's also a code that has been worked on and developed to be extremely flexible and applicable to a number of problems. And this has given it an advantage, and we're continuing to develop. We're looking for help in developing it, and it has the potential and is already currently helping users solve a number of problems. The graphics on the right-hand side, the top one is the MAX experiment, the thermal mixing validation simulation. The middle one has to do with the spacer grid validation and simulation, and the bottom one has to do with the pebble bed validation simulation. So you can see that the validation efforts and the application of NEC 5000 is broad, fairly broad, and getting broader. Here again, in this area, the reactor product line validation is key. It is for all our codes. This is the this code here. I mean, this slide here depicts the graphic from the multi-application small light water reactor experiment, and this is applicable to natural circulation phenomena important to small modular reactors. Proteus, that's another module in Sharp 3D suite, and it's an unstructured grid neutronics code, and it's the foundation for the Neams neutronics tool in the reactor product line, and it provides a complete neutronics analysis capability, including three-dimensional transport solvers, cross-section processing, reactor kinetics, and depletion. It involves the use of the high-fidelity cross-section module, NC²3. It can also leverage and employ subgroup cross-section, the subgroup cross-section module, which I think helps make it applicable to thermal reactors. It employs and utilizes a high-fidelity transport module UNIC. It can employ a kinetics module, and also makes use of the depletion module origin. And it's been around a long time, but this is an origin that it reflects a lot of advancements in recent years. So the MC²3 module in Sharp has been developed under Neams, and for generating fast reactor multi-group cross sections. They can be used for either conventional diff 3D or high fidelity Proteus codes. In this, of course, cross section generation is a significant issue, and this MC²3 helps us preserve the physics, helps build in the correct physics into the models that we're developing. And it can generate cross sections for widely different levels of fidelity, which is important. The current status, I think what we'd like, you can see right here. I won't read this for you. You can read this, digest it, and maybe seek out some lines of inquiry or questions from that. I would like to point out that it has we've developed a library that has gotten the latest information from the NDEF B71 cross-section library, and that gives it a particular advantage. And we invite you to take a look at our subscope in this area to see what you might be able to contribute. The needs are listed there, and I'm going to cover those when I get to that portion of the subscope. Diablo is structural mechanics code, and I think one of the things that makes it unique is that it does include a variety of contact modeling options. Modeling contact is always difficult, and they've done a really good job of it here, and I think that suggests itself to a lot of applications. Now you can see on the left, the graphic on the left shows the structural interaction between core assemblies and core restraint, and then on the right you can see the thermal deformation of core assembly during loss of flow transient. And the scale there is exaggerated so you can see the separation. It's certainly not that. It's certainly not that much in reality. The integration product line. I want to talk a little bit about this because this year we've added a subscope addressing what our integration product line does. We've got a lot of good tools from our fuels and reactor product lines, but a lot of times they require large computational resources. They can be difficult to install and require expert knowledge to operate. Our goal here is to be able to have an aspect of the program that integrates those tools and also can integrate them with current production tools that are currently used in R&D programs. And you can see a list of desired attributes that we're seeking. And you can see also where we're leveraging investments in, and the top one listed there is NEA. Since this is an area that is newly included in our scope, I just wanted to give you just a quick glimpse of the history. Of the IPL. We had some changes in our leadership and priorities, and it resulted in refactoring the IPL and what it does, and deliberating over our 5-year goals and our path to achieve them. It really led us to a place where we put as primary emphasis proactive customer engagement to ensure our relevance, and more importantly, deployment of our tools. In the near term, what this has done is has changed our interaction with the Advanced Reactor Technologies program and with the NRC. And I'll show you that in just a bit. This change in emphasis prompted us to take a look at a new concept, which we call the Neams workbench. The Neams workbench it's a way of making high fidelity tools more accessible, how to get them integrated into a workflow and manage that workflow, how to integrate the tools of varying fidelity, and implementing what we call a templating approach, which we think is unique. And I'll explain that. But you can see from this slide that we attempt to depict how both workflow management and the integration of tools, along with easier access and a better user interface, can go a long way into helping us not only deploy tools, but have them be fully integrated into R&D programs. And we take a snapshot here of Fulcrum. Fulcrum is the tool from Scale that we will be leveraging, using to develop our own interface with the Neams and the Neams workbench. And those will just give you some ideas you can look at on your own as to how we're approaching this. And I mentioned a templating approach. In the templating approach, this is a graphic that attempts to depict that. And for instance, in the engineering style problem-specific input, you might, for instance, say have a number of fuel pin size, and the dimensions, and some of the needs. Do you want high fidelity or low fidelity? Do you want power distribution, for instance? And that's fed in there to the template engine expansion, and that draws on a database say of codes like diff3D or Proteus. In this case, maybe you use Proteus, and then other aspects, other things that you might need, in order to develop and expand that template, which then allows the use of various codes together to get you the solution that you're looking for. You may have more questions on this, because I certainly cannot go into the technical details of all this right now, but Brad is available and willing to cover this with you. And I think it's important because we're asking for help in this area. So you might want to form some questions, either right away, or you might want to give it some thought and come back to us, because we really would like your help if you're so inclined. And again, summarizing the IPL, it's bridging the gap between two unique frameworks to extend multiphysics coupling with advanced tools, as you can see depicted here. Other things that I would like to share with you, even though they're not directly included in the scope, they are in the sense that the tools that underlie these other areas of activity are in the scope, and the help there will help these areas. A high priority for NE and for Neams in particular is the support of TREAT. Not only resumption of high power, short duration transit testing, but also the improvement of it, the enhancement of it, primarily by expanding the testing regime and allowing us to do more tests more effectively, especially in advanced fuels. In modeling TREAT experiments, we draw on a number of the MOVE-space applications currently in INL. You see depicted here. And we deal with dealing right now, we're looking at it in two ways. You've got the core behavior and you've got the experiment behavior. And we want to be able to model both. Another area of activity in Neams are high impact problems, and this is a growing area. This is where we work collaboratively with customers to solve problems that are of high impact, of importance to them, particularly industry, although not exclusively so. And I describe them here on this slide, and you can look at them. We have two underway now that will be finishing up at the end of 2017 or going into 18. And one is in accident-tolerant fuels, which supports the Nuclear Energy Advanced Fuels Campaign. And the other is a steam generator flow-induced vibration, that supports NuScale and AREVA. So we've divided our scope into 6 subscopes. Again, overall, we're looking for proposals that seek to improve our mechanistic models, our computational methods, our validation basis, code integration, and deployment for Neams tools. We need help in that area. So you see them listed here. If we take them one at a time, Neams 1.1, this is the lower length scale, atomistic and mesoscale modeling area. We definitely, as stated there, we want to improve our predictive capabilities, and we want to expand the phenomena of interest, and also extend the capabilities of Marmot to a broader range of fuel and cladding materials, and improve the validation basis of the code. In 1.2, I think this area reflects the need for advancements in material science. We want to be able to take those advancements, and to be able to implement them into Bison and improve its ability to predict fuel performance. I think here, as in the other scopes, we'd like to see proposals, if you're so inclined, that would couple capabilities. In this case, lower length scale to Bison. They basically use lower length scales to inform the engineering scale Bison. And as you can see, that in running Bison and Marmot, they can be coupled in several ways, or in a combination of ways. So core neutronics. This is an area that we where we have a number of needs. One of the things that we're looking for is verification and validation for a new capability, the 3D MOC or MOC capability, and the thermal cross-section capability. And the current production version of MC²3 has a 1D capability and fast reactor application only. We'd like to expand that. Since 3D MOC requires large computational resources and ultrafine group calculations, it needs performance improvements in terms of computation resources and numerical acceleration. The current procedure requires RZ geometry, whole core 2DANT calculations to accurately account for local spectrum effects when generating coarse number of groups. For example, condensing 2,082 groups to 33 groups. There are complexities involved in an RZ core representing the actual core, and the 2DANT transportation calculations are not efficient. So we need to improve it by coupling MC²3 with a whole core calculation capability of Proteus. The university teams are encouraged to contact the Sharps neutronics team lead at Argonne, and we will provide that. Brad will provide that contact in order to clarify the scope. So, thermohydraulics. In the thermal hydraulics area, we're looking for proposals that help develop and implement advanced turbulence models for turbulent heat fluxes and liquid metal fuel assemblies within NIC 5000. And I think that so this is the one, thank you. So the reason we need some help in this area is NEC 5000 has the URANS models implemented, but these include K omega SST, and K epsilon models, that one is less tested. These models have been traditionally created for fluids where the Prandtl number is about 1. But liquid metal coolants with very high thermal conductivity are different, and the Prandtl number there is more on the order of 0.01. And this affects the turbulence and temperature predictions. So standard RANS models don't work well for liquid metal coolants. So the focus of this call is on development of novel URANS and hybrid large eddy simulation approaches for the prediction of temperature flow in low Prandtl number flows. The models should be implemented into NEC 5000. That's important to us. And developers are welcome to also implement it in other codes for comparison purposes. And developers are encouraged here to use available experiments for validating and developing DNS databases with NEC 5000 or other codes. The focus is on wire-wrapped rod bundles and forced, natural, and mixed convection flow. Structural mechanics, we believe that we have some unique advantages with Diablo. We'd like to enhance those, and we're asking for your help as described in this subscope. The one thing I'd like to add to this is that for this one, if there are, with the products that you develop, that you propose to develop, we would like to see that proposal include a process where you provide your product as a module, standalone module that can be wrapped around Diablo but still maintained separately. One of the motivating factors for that is if there's some kind of proprietary information, it's kept exclusively to that module and doesn't pin Diablo down with containing that proprietary information, so that we can continue to still share Diablo openly. At the same time, we want the benefit of your work, so if you provide it as a separate standalone module, that helps us. And that is specified in the scope that is being published, so you can see that for yourself. The new area, integration and demonstration. Proposals are sought to integrate high fidelity as well as conventional tools into the workbench. And I think one other aspect of this I'd like to highlight. You can read these for yourself, and I think they're, with what we've talked about, you should either be self-explanatory or at least suggest the questions you need to ask. But I'd like to point out that that we're really looking for ways to provide convenient access to uncertainty quantification. And without that, there's a lot of advantage that's lost. Let's put it that way. So that's it. I'm open to any questions right now. Brad Reardon is here if you have a technical question that he can field, and certainly we can follow up by email and other ways for other questions you might have.
Dan, in Neams 1.3, is there an interest in new methods for quantifying uncertainty and criticality and coupled criticality burn-up simulations that could be used to develop modules for existing codes?
I think that would be a yes, but I'm going to let Brad chime in on that if that's okay.
Yeah, Brad, if you would join Dan so that you can share the mic.
Because there may be some nuances, technical nuances there that he might be able to address that I can't.
Okay. Yeah. So I'm sorry. Would you mind repeating the question?
In Neams 1.3, is there interest in new methods for quantifying uncertainty and criticality and coupled criticality burn-up simulations that could be used to develop modules for existing codes?
Yeah, I think there is interest in definitely uncertainty quantification, especially for burn-up capabilities. Generally, the core neutronics do not address sort of traditional criticality safety applications, but it's more of a reactor physics application area.
How many projects do you anticipate funding in Neams 1.1?
We're going to. That's an interesting question. It's hard to say. I hate to give you that answer, but we typically have been able to award 5 or 6 projects per year, and that can change, but that's a typical range. And with this number of scopes, we would hope to have a representation from each subscope. So we might be down to just one award per subscope, but there's also the possibility that two project proposals in one subscope area are so good and so needed that we might do that. But we definitely want to try to have a broad range of these subscopes represented. If funding situation changes and our ability to invest more increases, we will definitely. We're not putting a cap on it. It's an implicit cap because of our funding restrictions.
In Neams 1.4, can DNS be produced by a code other than NEC 5000?
That question, I'm not sure of all. There's a lot of questions I might have about that question. But let me say that what NE in general and Neams in particular is interested in is investment in the Neams capabilities, expanding them, applying them, extending them, developing modules that can wrap around them, things that are relevant to Neams. So as such, we're trying to avoid an instance where NE is funneling dollars into developing new codes outside of Neams when Neams is our primary area of investment for these new advanced capabilities. This does not say that we can't apply existing codes to solving problems within projects, obviously, or developing those codes, those existing codes, enough to apply to the problems as necessary, or where Neams is not problems in which Neams is not working, but in those problem areas. I hate to be that circumspect, I don't want to ever say that there isn't some code that could be written out there that could be used as an adjunct with NEC 5000. I wouldn't want to presume that or assume that there's no room for innovation. But we are going to be prioritizing proposals in this area that deal with NEC 5000, enhancing it and extending it in accordance with the subscope description.
So to clarify, the wording new tailored DNS data set are encouraged must be done with Neams tools only.
What do you think?
Well, I guess we'd have to look at the proposal carefully. We'll judge everything fairly. But the intention is that we are enhancing the Neams tools, not developing independent tools.
Certainly in that scope, we allow for the development of these things to be applied to other, that could be applicable to other codes. As long as they're applicable to NEC 5000, it's certainly, if they're applicable to other codes, that's certainly a plus. So.
Is there any interest in new high-resolution experimental data for Neams 1.4?
I think so.
Yeah, I'm looking at this to see if it's why that would be ruled out. It's certainly not intended to be. So yes, yes, we would be. That's a good question.
Can the Neams 1.1 work scope include experimental work?
In 1.1, yes, I think it could. We also are interested in that. I think that goes to improving the validation basis. That can be done in a number of ways, but certainly we'd be interested in seeing proposals that would provide our experimental data that would support that validation.
Your next presentation.
Yeah, because that's with this NSUF. Yeah, we have another scope that we'll be presenting on NSUF, but NSUF aren't the only facilities where experiments can be run. So if you have something, there's an NSUF person in the crowd. I just stepped on it. Okay, so, but yes, in this scope, that would certainly be welcome.
How many Neams proposals were submitted last year?
I'm tempted to say I lost count after I read them all, but I believe we had. I think we had 60-some pre-proposals, and of that we ended up getting between 27 and 30 full proposals.
The last question I'll answer, is it possible to find a list of currently funded NEUP projects and PIs, including Neams? You can find that information on neup.gov. If you go onto the R&D tab, there's a list of years with the subheading funded projects, and Neams is separated into its own section, so they're especially easy to find.